Welcome to Above the Line. This is where I sit down with the Futurum's research team to break down the technology shifts driving the market and tell you what it means for your portfolio. Today, I'm joined by Brendan Burke. This is Futurum's research director covering semiconductors and emerging tech. Brendan just published a full report on orbital computing through Futurum Research, and everything we're about to walk through comes straight out of it. If you want the numbers behind this episode, the report is where they live. Welcome, Brendan.
Hey, Shay. Great to be speaking with you.
Appreciate you hopping on. I'm excited to kind of walk through the 5 charts from the report. I kind of want to start with the prize. Let's start with the chart that made me want to do this episode in the first place. Your team's bull case right now is $3 trillion that are going to go into AI data centers in 2030. And this chart says a full third of that could be looking up. Walk me through it.
This is really looking at the off-grid portion of the data center market in 2030. The reality is that the data center capex is bifurcating into grid-tied and then off-grid data centers that have different cost profiles, different needs for gas turbines, solar panels, switch gear, and a lot of the power equipment that's currently in shortage. The cost profile is going to differ, and ultimately, when a hyperscaler looks at where they're going to put a GPU, whether it's in an existing shell, a new shell, or in space, it's going to come down to what the costs of each of those deployments are. And when you look at a $3 trillion bull case for 2030, that goes to both the number of gigawatts that hyperscalers have demand for, and then also the cost per gigawatt. What's most material for space data centers is that we're pushing much higher in terms of what these gigawatts cost. Jensen has recently reinforced his guidance that we could be looking at $100 billion per gigawatt at the high end in the next generation if you're deploying the full superpod system for Feynman. And at that point, you start to look at a third of these systems. If you have to power a 800-volt rack off-grid, that's going to be incredibly costly per gigawatt. And it's at that point where I think the hyperscalers will look at those off-grid data centers and say, well, maybe we could go somewhere where the land and power are cheaper than here on Earth. And so that's when space starts to make sense.
Where does this math actually kind of break first? Is it the launch curve, the hardware curve, or the grid getting unstuck?
I think first and foremost, it is the installation costs of data centers. If that levels out somehow and we find a way to unlock more grid capacity, that really reduces the whole economic case and pushes this orbital transition out by years. But at the satellite level itself, what we're really looking at is the ability to launch a high volume of compute on a recurring basis. And to that extent, the key trigger is going to be improved launch economics and a more regular frequency of orbital launches. And from there, it just depends how much compute we can pack onto each flight.
A $1 trillion market in orbit, though, also means somebody has to build a data center in space. So the next topic I want to look at and talk about is one of these things even made of compared to the data centers that we actually know today. This is the bill of materials side by side, same 5 subsystems every data center needs. We're talking about power, cooling, compute, structure, and interconnect. In orbit, every one of them is answered completely differently. So, Brandon, walk us down this table.
I think each of these layers is its own system. When you look at power, cooling, compute, physical satellite structure, and then the interconnect between satellites. And each of them has unique engineering challenges that need to be overcome to make the collective system work together. And so, first, with power, the benefit of putting satellites in space is you get a lot more energy efficiency from it. You can get 5 times the yield of a similar solar panel on Earth. And so you're disintermediating a lot of the uh, fossil fuel equipment that's most commonly associated with off grid data centers today. And so that eliminates a lot of the equipment shortages that we have on Earth, because solar arrays are not necessarily in a shortage compared to the rest. And it's an area that SpaceX is actively working on manufacturing. And so that's really the unlock, is that lower cost of energy on a uh, per unit basis. And then cooling is needed on both Earth and in space. We talk a lot about the challenges of radiators and dispelling heat in space, but it's also a concern here on Earth, where we're applying chillers, cooling towers, and gallons of water in the order of, say, a restaurant, more so than a city when it comes to a individual data center. And then in terms of compute, we're looking at very similar compute infrastructure. We've recently shown that Jetson GPUs are feasible to operate in space for 5 years on a lunar mission. And so we're becoming more suitable to put GPUs in space and harden them against radiation. And then in terms of structure, need a shell for both. A satellite is a shell in terms of the ability to deploy compute and then maintain it in orbit. And last, an interconnect, likewise, scale across is the big challenge. How you connect multiple servers together in a scale out domain and then scale across between different units. And uh, in both cases, optical is the way to go at long distances. And in space, that tends to pertain to laser based links as well as downlinks to the ground. But fundamentally, you're looking at the similar engineering constraints. So it's just different materials and a different context. But when each of those links reaches parity with its terrestrial equivalent, you start seeing that space can make economic sense.
Yeah, I mean, I have a quick question for you, actually. Of these 5 rows, I have a specific layer that I think is the most underappreciated, but what do you believe is the most underappreciated by the market right now?
I think it's the ability to interconnect clusters together via laser links. We often start with the energy availability in space, which is terrific, but a real constraint on Earth at the moment is the glass for fiber that's needed to scale across, and then the construction challenges of tying multiple data centers together. That's actually a lot more feasible in space because we can use lasers. There's not as much interference in that context, and so that allows us to scale up the kind of coherence of a cluster in space, even beyond what we can do on Earth. And so that's an area I think we're going to see a lot of exciting research on. It's a focus of some of the most innovative companies in the space. And that really goes to the ceiling of whether we can look at gigawatt data centers versus terawatt scale clusters that are able to all communicate with one another and carry out jobs in sync.
I think there is definitely that layer is one of those generally better layers in orbit that I think that a lot of the market is kind of pricing in terrestrially right now, the data movement theme. But one of the biggest questions that I always get regarding the space economy or the orbital computes TAM, if it's so good and if it makes so much sense, why isn't anyone building it at scale yet? Because today the numbers are pretty brutal, which probably shows why there is a little resistance towards orbital compute. So here's the honest chart. I mean, if you price out a gigawatt today and orbital costs around $75 a watt against 17 on the ground. That's 4.5 times more expensive. So, Brandon, where does the money actually go?
$75 per watt is significant. It does start to actually line up against the 100 billion per gigawatt, $100 per watt that Jensen has mentioned. So this is just looking at the physical infrastructure needed to put a megawatt of compute in space. And most of the cost here is the launch. It is the rocket that takes compute to orbit. Another reason why it's the biggest lever to drive down costs. And from there, we're looking at the satellite itself, the bus that actually carries the compute. The other costs that come into play here include any non recurring engineering for installation. And then you're also looking at the loaded cost of radiators and solar panels that have to be loaded on to the satellite. And so, that reaches a level that's far above what it costs to build a data center today. But as our terrestrial data centers get more complex with more custom engineering for each system, it's possible that this could look fairly similar as terrestrial costs continue to go up.
I know this is more about orbital compute, but when you were talking just there, makes me think about instantly Starship. I think that this right here is exactly why the TAM for the AI part of SpaceX's IPO roadshow was just so massive because launch is half the bill. So I want to ask you, like, is the whole thesis just a bet on essentially if Starship unlocks the key to orbital compute?
It is the necessary condition right now. It's not sufficient on its own, I don't think, but it is an assumption that the industry is making that the historical rate of progress of launch costs will be continued. And you think about what it would mean to slash this cost by 10 times. You then get to more of a 20 to $30 billion cost per watt or gigawatt to put compute in space, and things get fairly close to parity. Because there's going to be some fixed costs, there's going to be some advanced equipment, and some failover redundancy that's needed in space. Maintenance is going to be an inevitable part of the cost structure as well. But fundamentally, SpaceX is the unlock for this industry at present. It's just a very well capitalized company and one with some of the best engineering talent in the world that might actually be able to pull it off.
Yeah, I mean, Elon shoots 100 for 100, so I think that he will eventually solve it, which is huge because that's right now more than half the entire cost problem is just getting the mass to orbit. So once that unlocks the ability to do that, it's going to be massive for that whole space, which is why I think the next chart that we're going to talk about is going to be what the whole thesis relies on. This is the launch cost curve, and it's the hinge for everything that we've talked about so far. And I think that from the shuttle to Falcon 9 reuse is already something like, I don't know, 900x collapse in cost per kilogram. So I think the green line is the break even where orbital compute starts to really pencil in around $500 a kilo. So Brandon, like, how real is the rest of this curve?
Depending on consistent reuse, being able to launch multiple Starship flights per day in some cases, and then being able to load 5 to 10 megawatts on a ship per launch. And so then you start to get to the point where you can actually get a significant amount of payload to space on a regular basis. The challenge here is all in the rocket science. What we've seen is that this is a plunging cost curve. What we have seen reuse be proven with Falcon 9. We are at a point now where even if you look at 1,500 per kilo, it starts to be cost competitive with some of the most frontier data centers. And When we look at the opportunity to bring that down by a third, it becomes cost competitive with many gigawatt scale data centers. And then the goal is clearly to push launch costs closer to 100 per kilo, and conceivably even lower. But I do think that 500 per kilo is a point where we're going to start seeing some production compute launched to orbit. And it's an area where you have to follow the direction of travel rather than fretting about every launch and test ship that goes up.
Space is hard, folks, and it's only going to continue being hard. And I think that you're going to consistently see these like failure investigations or payload and integration issues, reuse delays. I mean, just like a Blue Origin, like doesn't matter how much money, aka Jeff Bezos, has, you can't just throw money at a problem in space and expect it to solve itself. So like there is a real chance that Starship underdelivers on cadence. And I think that the first thing when that happens isn't that demand's going to break. So I just have to caution everyone that even if there's any kind of turbulence along this trajectory, it's a bump. It's not a wall. So like what's your honest take, Brendan, on the specific timeline risk for this?
I think that with the engineering intensity that's being dedicated to this mission, the overlap between SpaceX and XAI, and the capital that's been infused into the company, as well as progress that we've seen in recent launches as far as rocket reentry and reorientation for landing, this seems like a challenge that could surprise to the upside as far as the ability to uh, do rocket reuse within the next 5 years, but as soon as within 2 years. And there's still going to be data and safety measures that have to be collected and taken before we scale this up to a greater degree, and maybe even a higher stock price, which we'll have to get your view on as to whether SpaceX is going to have access to capital markets needed to really go full bore on launch frequency. But given the momentum around the company, I think this is an area where we're going to see a lot of progress.
Yeah, I mean, what I hear is volatility. I think that good or bad, there's going to be volatility, especially in SpaceX stock. So it's going to be something to monitor for sure. But we just talked about launch is the hinge essentially. But you said it earlier yourself, like launch alone doesn't really close that gap. There are actually three curves that all have to bend at the same time. That's the last chart, and it's really the checklist for this whole thesis I want to talk about. Launch is going from $1,400 to $200 a kilogram. That's nearly 7 times cheaper. Seeing satellite hardware from $22 to $11 a watt, which is half the cost, and then specifically power doubling from 40 to 80 watts per kilogram. So miss one and the whole model breaks. Brennan, who actually does the work to bend these? Like, what are the components underneath each of these curves?
I've set some aggressive targets here. I mean, my goal for the cost per watt would be to really get down to the 50 billion per gigawatt all in. That's we don't as an industry just want SpaceX to be doing this. We, something that Google's looking into, something where Amazon has a strategy, and it's going to be those hyperscalers and labs that determine whether this is a terawatt scale opportunity versus just one company. And I think they're going to be looking for getting even lower than say break even, but really to a positive ROI at around $200 per kilogram, and that's going to really look at 150 tons per launch, and so they can get towards 10 megawatts per deployment, and so that's going to really come from the rocket engineering itself. But I think equally as important are on satellite hardware and then also solar efficiency. Those are areas where there's got to be innovations in material science and then systems engineering to get better performance out of the materials that we have with improvements in the manufacturing process for each of those areas where SpaceX is making a lot of gains itself. But I think particularly in the solar side, there's room for suppliers to bring in thin film arrays, as well as lighter liquid radiators, and then higher efficiency, both solar cells and chips that can get more energy to each chip. And so, those are areas where I think we've seen similar efficiency gains in the past. That's why we've had such mass deployment of solar on Earth. So we just have to look for a collective effort of the engineering community along with the physics simulation to make significant gains and make it over in a timeline of multiple years instead of multiple decades.
Amazing. I mean, we covered a lot. I appreciate you hopping on. But before I let you go, I want to know like one thing you're watching over the next 90 days that tells you that this thesis is on track or potentially slipping and the goalpost needs to be pushed further out.
I really view this as a collective effort. I think SpaceX is going to face competing priorities in public markets, and I'm really looking for the rest of the industry to define their space strategy, whether it's outlining a roadmap for space-based silicon, physics simulation solutions, reducing satellite costs, and improving the efficiency of satellite solar arrays. And then looking for pilot customers who are interested in testing this out. And I think these are areas where we can make progress today. We can set engineering roadmaps, and then as we get more launch data in, scale some of those strategies up. But seeing a lot of progress today, and I think that that really tees us up for an exciting few years coming up.
Well, Brendan, this was great. I know this is not going to be the last time we talk about orbital compute. This is a theme that's very early. It's got a ton of runway, and there's going to be a lot of winners in this arena, especially in the fluid stage of the space economies. The full thesis, all 5 of these charts, and the cost model behind them is in Brendan's report at Futurum Research. Go read the real thing. Now stick around because I'm about to do what Brendan is unfortunately unable to do, and that's putting tickers on every layer of the stack. All right. Well, Brandon walked us through the layers of the stack, and now let me take a couple minutes and go layer by layer through the names I believe are the biggest beneficiaries of the orbital compute buildouts. Not just for the next 5 years, but like I've been saying, this is a very early vein with plenty of runway. So we're talking decades here. And before I get to the specific layers, I kind of want to give a voiceover on what do you think about orbital compute as a whole? Because this is the number one question I get these days, not just from the community or followers, but media. I mean, space economy is becoming a very real thing with the SpaceX IPO. That's causing a lot of media attention, and especially in an arena where there wasn't really seriously covered in the past. So I think it's really important to call out that when we talk about orbital computes, it's not just a simple data centers and space theme because there's a whole full stack that has to be built in layers. And each layer has a very different risk profile, timeline, and the way you should anticipate who benefits from what. And I think the most important part is orbital compute will not be a near term AI training story because I still think that training models require a ton of GPU clusters, extremely fast interconnect, reliable power, low latency, and serious cooling, which is already difficult enough terrestrially. And it's going to be dramatically harder in orbit. So I think for this decade, the more realistic opportunity is going to be inference at the edge where satellites process imagery, sensory data, defense data, telemetry directly in orbit before deciding what actually needs to be sent back to Earth. So that makes the theme really hard, but the order of operations matter, and that's why we're going to the layers. Let's talk about the first layer, compute clusters. So this is probably the most obvious layer, and this is where we talk about NVIDIA, AMD, even I guess the Amazons, the Googles of the world, the Microsofts of the world, SpaceXs of the world. This is the part where everyone thinks about when they hear about orbital compute. It's like GPU or TPU clusters running in space and eventually acting like orbital data centers. The problem is that this is probably the least mature and more capital intensive layer because one GPU in orbit is a proof point, but while a scaled orbital compute cluster requires a ton of power, cooling, laser interconnect, satellite reliability, and utilization all working at once. It's very difficult, very capital intensive, but NVIDIA is the best player for the space because they already have H100 chips as part of the orbital compute narrative through StarCloud. Uh, then Amazon matters because through AWS outputs, and the idea that cloud hardware eventually extends into space-based infrastructure. You have the similar thing with Google through Project Suncatcher, and the long-term possibility of running TPU-based compute in orbit. And they also obviously have SpaceX because they own launches, satellite manufacturing, potentially the lowest cost path towards putting compute hardware into orbit at scale. And now they have a compute leasing business. So like I think that this layer is probably the biggest dream layer, but it's also the hardest layer to underwrite today because of the capital intensity and the requirements needed. So I would view it as more as a long-term optionality rather than a near-term revenue story. Second layer I want to talk about is the semiconductor hardening. This is probably one of the most important layers because none of the orbital compute thesis works unless advanced AI silicon can survive radiation, launch vibration, years of operation without normal data center maintenance. What I mean by that is on Earth, if GPUs fail, the operator can replace it. But if that happens in orbit, failed chips can ruin the economics of an entire satellite or compute node, which means raw performance just isn't enough. Real bottleneck performance is going to be needed to survive space. And this is where I talk about the TSMs of the world, AI factory behind the chips, ASML, the equipment layer underneath the foundry layer. And obviously, you have to include Intel. It's long shot, Trojan horse. They still have to figure out their terrestrial advantage on foundry, but if they do, space could be a secondary thing for them. Let's talk about the next layer, which is optical interconnect. So this is probably the layer I would watch most closely, and also the layer I view as the most underappreciated by the market. I think Brendan also agrees with this sentiment as well, because orbital compute doesn't work without extremely fast data movement between satellites, compute nodes, relay networks, and ground systems. I mean, on Earth, optical interconnect is already one of the most important AI infrastructure bottlenecks because the GPUs, racks, and data centers need to move huge amounts of data. But in space, the problem becomes even more important because the network itself becomes a connective tissue of the orbital compute economy. So, what I mean by that is if satellites are going to act like a distributed data centers, they need the laser links that can actually move the data quickly and reliably between nodes. Otherwise, each satellite is just an isolated box rather than part of a large compute fabric. And I think the beneficiaries of this layer is going to be the same ones that are on Earth. I mean, Broadcom is going to be the king, but you also have the Coherence, Lumentums, even Applied Optical, the Credos, the Marvells, the Stereo Labs. Like everyone who's benefiting from the terrestrial optical interconnect bottleneck is going to also benefit in the space optical interconnect issue. The next layer I want to talk about is multiphysics simulation. This is probably the least discussed layer, but you can also make the argument that it might be the most defensible because you cannot cheaply iterate hardware in orbit. Inside a data center, a company can test, adjust, replace parts, redesign the airflows, and keep iterating all the requirements needed. But in space, every mistake is more expensive because every hardware has already launched. So it may be impossible to repair. That means an entire orbital compute system has to be modeled before launch, including thermal management, radiation exposure, launch vibration, power generation, like satellite bus designs, like all these factors have to be just not 99%, but it has to be like as close to 100% reliable before you send it up in space. And you got to think about synopsis, cadence when you talk about this layer. Even honestly, Palantir. I mean, Palantir would matter because operational software side of this issue, when you have orbital compute, is not just require hardware design. They require systems integration, like mission planning, data orchestration. So like that is right up Palantir's wheelhouse because they make complex assets look easy to the end user. I think that this layer is obviously all about capital efficiency, but it's the least appreciated, but it's still very important. The last layer I want to talk about is vertical integrators. So this is probably the layer that has the most durable equity value that will accrue, but it's also probably where the most execution risk sits because vertical integrators have to make the full system work across chips, satellites, launch, power, cooling, customer demand. Like there's so many elements to make vertical integration work. And it matters a ton because orbital compute is a systems problem. It's not just a prog problem. And the company that controls more of the stack can lower the costs, improve reliability, move faster, and capture more of the economics. Right now, it's a two-way race in this arena, this layer. It's SpaceX is by far the king, most important name because they already own the launch layer, satellite manufacturing experience, Starlink, Starship's going to be a big unlock for orbital computes. They already have the optical network experience, and Starship again. I'm going back to that. I mean, Starship is the cost curve for this whole layer, and I think that means if SpaceX can be both the enabler of orbital compute market and the most dangerous competitor inside it. Really interesting place to be in. Obviously, you can't talk about this layer without discussing Rocket Lab, which is probably the most pure public market exposure to this layer when you have launch, spacecraft manufacturing, satellite systems, and just the broader space infrastructure build outs. So yeah, I mean, I think that this is all the layers that we talked about in the call with Brandon. It's the reason why every layer is just so uniquely positioned and it has different timelines, different risk parameters. I think that it's unfair to call orbital compute as just data centers in space tomorrow because there really is a massive stack build out where inference comes from training. Hardened chips comes before large clusters. The optical links matter a ton. And the vertical integration story eventually determines who can turn this into real infrastructure. But like I said, this theme is very early. It's very fluid. A lot of these new winners can enter these layers. And that's why it's really important to follow the latest and greatest research because what is true today might not be true in 3 months. So thanks for tuning in.